Okay, hello. Hello and welcome everybody to our autumn series of the Earth Science and Engineering departmental seminars. So in the seminar team, I've been joined by Catherine Hadler, Valentin Laurent and Dylan Rood, and I'm having great help from Victoria Murphy as well with this transition to going online with these seminars. Also, we've been setting up together the spring term speakers as well. So we've decided on the Microsoft Teams live event as our platform, and so there may be a few teething problems, so please bear with us and see how we get on with this particular platform. So now briefly on some housekeeping issues. All attendees can ask questions, but you should see the tab on the right hand side to do this. So to do so and ask questions, you will need to type your questions. That's one difference between the other platform. So after the talk, there will be a live Q&A session, and the chair will be relaying the questions to our speaker. So at present, the link for attendees to join the event, we've just used the Earth Science and Engineering colleagues, but we do also plan to invite obviously the rest of our connections within Imperial. They'll be welcome. And the seminar will be recorded for archiving, and this will be set up on a Earth Science and Engineering YouTube channel. So now finally over to the main business of the day. I'd like to welcome Professor Anne Muggeridge, and she will be introducing today's speaker. So thank you. Over to you, Anne.
Thank you, JP. Welcome to everyone. Yes, I'm the host for today's seminar. I'm absolutely thrilled to bits to be welcoming our very own homegrown Adriana Paluszny, if she'll forgive me my pronunciation. I'm sure everyone must know Adriana through her work in the department and also through her work on the Watson Forum and Equality and Diversity. For those of you who are less familiar with Adriana, she's been with us since she did a PhD here in computational geomechanics, and has now become a senior lecturer and is a Royal Society University Research Fellow. And her main focus is on the robust numerical modeling of fracture growth in 3 dimensions, which has a host of applications for fluid injection, fracking, drilling, and generally in computational fracture mechanics. She's going to do something slightly different today. She's not going to talk so much about her numerical modeling. Instead, she's going to share a presentation that she gave only yesterday, where she was the external focus for the Shell Global Awareness meeting, the first in this year's series to senior folks within Shell. So with that, I shall hand over to Adriana, where she'll be talking, as you can see, about Caprock integrity and public perception studies of carbon storage in depleted hydrocarbon reservoirs. Thank you, Adriana.
Okay, thank you very much for that introduction, and good afternoon, everybody. I will be giving a talk today where I will try to drive you through the literature that connects Caprock integrity studies and in general geomechanical studies with the public perception studies that we have available in the context of carbon storage in depleted hydrocarbon reservoirs. So what we wanted to do was to understand what research has been done in this area and what research should we do going forward in this area to best aid carbon capture and sequestration, for example, by injecting it into depleted hydrocarbon reservoirs. So the talk that I'll give today is summarized in a paper that has been published already in the International Journal of Greenhouse and Gas Control, and the title is the same as this presentation. What this paper did was to go specifically over a number of pilot studies across the world that essentially tried to inject CO2 in various forms into brown reservoirs, so reservoirs that have been in the past either oil or gas reservoirs. And there are a number of collaborators here, and so I'd like to take a minute to acknowledge them, as many of them are based in the British Geological Survey, and some of them are former postdocs in our group, so Vasily Ketseparli and Said Salimzadeh, who were based at Imperial for most of this work. And also Lorraine Whitmarsh and Dimitrios Senias are worth mentioning because they are the social scientists that are related to this work. So in a sense, this work brought together a number of different types of scientists. So it was definitely, for me, a new type of activity. And the work is subdivided into four. First of all, we look at the different pilot sites, and we try to explain in brevity how they were funded, why they either closed or were cancelled, and where they were located and so on, how big they were and so on. Then we did a deep dive into the literature looking into that. Then we did also a deep dive into the literature looking into public perception studies that were either generic or in any way tied to these pilot sites, maybe temporally, maybe geographically, maybe directly naming these. And we looked at as well, on the other hand, the characterization of the rocks at these pilot sites. So how much data was there before and during the development of these sites, was from the geomechanical point of view. So was there a lot of information about the rocks? Was there information about the reservoir or the caprock and so on? And on the other hand, we were also looking at the types of models that were either predicting or evaluating this injection into these reservoirs, and looking in particular at geomechanical aspects of these sites. And the idea of this was to try to find connections between them, connections between geomechanical studies and how these percolate into public perception, and how that then affects the technology and the viability of this technology at a larger scale and into the future, going into the future. And this was part of a large of a project funded by EPSRC, which already ended a couple of years ago, that brought together these three teams, the Cardiff, Imperial College, and the BGS. And this paper was essentially one of the deliverables, or one of the outputs of this project. So of course, the teams that were concerned with this project did research in these different things, right? So the team on social perception did some surveys and some quantification of the perception of CCS in depleted reservoirs. The team at BGS was characterizing rocks from North Sea candidates for storage. And we were conducting modeling with our simulator, the ICGT of these sites, and another site as well, and of a North Sea site, and also tangentially on a site in Israel as well. So even though we were all focused technically in different subjects, at the end of the day, we tried bringing all of our findings together and try to understand how this project would help us understand the bigger question, and try to formulate what the important questions going ahead are. And so this is a rough scheme of what we found, and I will come back to this later. But essentially what we want to do is we want to understand what the relationship between these pilot sites are, which are in the depleted oil and gas reservoirs. Some of them are onshore, offshore, but they're all considered to be brown sites, so sites that are already sort of polluted in a sense. And we want to understand how this then goes into public perception, and through the lens of geomechanics, and to understand why they are connected, how they are connected, and what we can do to improve the feedback mechanisms between these two. So as you see here, the two main subjects that we will also be talking about, the characterization of rocks and the simulation of the sequestration, are very much at the root of what the evidence is. So even though geomechanics cannot directly influence public perception, and the work that we do does not really feed into public perception directly, it does feed into the evidence that we need to produce in order to eventually reach the public. And we needed to understand how those things are related. And I'll try to drive you through the work that we did through those years. So this is a list of the projects that the pilot sites that we looked into. The two first are the only ones, so Snovid and Helets are the only ones that are still active from this list. And one of them very well known, Snovid in Norway, and the second one, and slightly larger as well than the second one in Helets, which is much less well known, which is based in Israel, but is also currently active. There are a number of projects as well that are on hold here. Notably, for example, Schwarze Pumpe in Germany and LAC. And these are, for example, important in the context of this project, because Schwarze Pumpe was received with a lot of public opposition by the German public because it was related to coal production, and LAC was quite successful because it was measuring leakage rates and couldn't detect any leakage during the injection process, which was very good in the big picture of these depleted sites. Now there are also in this list a number of on hold projects and a number of cancelled projects. So the three last ones, and Peterhead as well, are cancelled projects, and there are slight distinctions between projects that are on hold and projects that are straight out cancelled, right? But one can regard those projects that are on hold as projects that have been cancelled, because for various reasons, including public opposition or funding restrictions, these projects were shelved, hopefully to be revived later on. But other projects like Hunterston and Barendrecht, they were outright cancelled. They faced very strong public opposition, and FinCap faced financial difficulties. So I didn't mention all of the projects that had financial difficulties, but a lot of these projects that were set on hold also were frozen because of lack of availability of funds. And one would think, what does geomechanics have to do with funding, and why should we care about funding? And it turns out that actually it feeds into the decision process of funding mechanisms, and it is related as well to public, not only to regulations and policy, but also to public perceptions, which also then feed into the financial scenario of these projects. And pilot studies are really important because these pilot studies, they allow us to study the operational constraints and the effectiveness of the technology, but also they allow us to validate numerical models, which are some of the main predicting tools that we use for for our decision mechanism. And they also allow us to gather data about rocks. So they allow us to get samples and test those samples, which then might feed into maybe analytical models or other types of models. So they're really very important in the process of substantiating this technology. And what one can find, the first thing that we could find across the board is that the fear of leaks is usually quoted as a common factor of concern for the public and for financiers and regulators and so on. So the fear of leaks. So you can see there we have two words: fear, which is irrational, and perhaps leaks, which is something that we can quantify. So this is essentially tied through risk, through the quantification of risk, both technical and financial, and feed both into the liability and the social acceptance of this technology. So the liability, so if I want to fund not only a large operation of CO2 sequestration, but even fund a pilot test, I need to be aware of what the costs of any mishaps would be, and what the legal liability and financial liability would be on perhaps things that happen after the end of the pilot project. So perhaps government regulations may change, and companies that did inject CO2 under certain conditions are later to be punished financially. And so all of these risks go into financial modeling and are also tied into not only the public perception, but also the geomechanical analysis. And so while we were doing this work, and because we are, let's say, scientists that usually deal with a lot of numbers, so as not to separate social sciences from other sciences, we wanted as well to create a database of all the information that we could find of those pilot sites, so that we could have a place to go back, so that we could share this information with other groups doing numerical models as well, and we could perhaps over the years populate this table. And what becomes apparent here by looking at these two tables, the upper table is looking at the reservoir properties at these pilot sites, and the lower table is looking at the Caprock properties at these sites. What becomes really apparent immediately is that the upper table is much better populated, much more populated than the lower one. So there's much more information about the reservoir, and you would expect that, because it is the pay zone for operators and companies that deal with these. So they really want to understand what the pay zone is, what the reservoir is that contains the asset. And the Caprock is much less well understood, and if you look into it in detail, you'll find that for some of these fields, for example, the Otway field, there's quite a good characterization across the board, and for others, there's just barely any information, any geomechanical information of the Caprock. And much less is there any information of the heterogeneity or the changes in the Caprock and so on, which we also suspect might have an influence. So this lack of data has a spillover effect on the modeling, right? Because if you don't have data, then that constrains the type of models that you can conduct, and it also constrains the predictive power of those models. So this essentially summarizes this. You can see that the information is lacking. There's absolutely no information about heterogeneity. So are these Caprocks completely homogeneous, or do they have strong heterogeneities and so on, which all will contribute to certain extents to the capability of the Caprock to withhold any leaks. And what you see here on the right as well is that for fracturing data, which is data that we need the most, this UCS here, this column here is particularly empty. So that that means that when we are looking at the risk of a Caprock failing, we really have to make assumptions as of what the properties of these Caprocks are, because the data are lacking. And this is something that we suspected, and we sort of knew this. We hoped that during the deep dive into the literature, this would somewhat change, but this picture didn't really change during this study. Then the second part of the study was about understanding the numerical modeling of these pilot sites. So we're looking at numerical models, not of CO2 sequestration in general, but rather models that were specific, or papers that were specifically presenting results to do with these pilot sites that we were interested in. And one thing that I should mention that I didn't mention before is that these pilot sites were chosen with very strict criteria and not to include any EOR sites, because we wanted to understand, so EORs are enhanced oil recovery sites, so where you are perhaps where you are retrieving hydrocarbons and injecting CO2 as a means to optimize that retrieval. So of course that's another type of sequestration as well that results in the trapping of some of that CO2, but these were not considered as a depleted reservoirs in this context. And one of the reasons was that we decided that the very strong link in EOR, in these enhanced oil recovery cases, the very strong link between economic profit and hydrocarbon production and the sequestration of CO2 would overshadow any of the public perception links that we could find, because everything is dominated by the public being antagonized against anything that progresses hydrocarbon exploitation. So that, for that reason, just forgive me, I want to say that before, but for that reason, EOR sites are missing. That means that most, if not all, of the sites in the US are not here, because all of the depleted injection to depleted reservoirs that we could find were always tied in the context of EOR. So having said that, when we looked at numerical modeling of the pilot sites, we were looking at specifically at this geomechanical modeling of the sites to try to understand how and what type of numerical models were being used, and if they were being cross-compared or how they were being validated. And what we found is that most of these, including here our simulator, the ICGT, I should highlight that, are validated, thoroughly validated on their own and independently, but we could not find at the time of the publication of this paper any benchmarks that actually looked into fracture and fault propagation linked or not linked to leaking during the thermohydromechanical deformation of these reservoirs. So there are some, there's a lack of these types of benchmarks that would also feed into the system of regulatory and social perception. And then this other table, this is the last table I'll show. This table brings together all of these sites and all of the studies that were related to these sites. So the first thing to notice is that usually they use one or two simulators. Some of them do use multiple simulators. But the other thing to notice is that there are very few. So we can fit them in this slide, which is really surprising. We thought actually that we would find many more. There are a huge amount of very generic studies, but specific studies related to the pilot sites are scarce, and they don't exist for all of the sites. So that's another thing. So if when assessing the evidence base for the pilot site, the regulators, the financiers, and these people that are evaluating the risk of these pilot sites will be looking for these very specific sites, very specific publications that are related to these sites. And the other thing to notice as well, which is perhaps not immediately clear from looking at the table in a screen like you're doing now, is that a lot of these studies are looking at the failure of the caprock, the breakage, the growth of fractures, the movement of faults. So and these, we know in the technical context, are precursors of induced seismicity and of leak, which are those common factors to all of these sites and the public perception of them. But they don't really go into the nitty-gritty of trying to quantify the leaks. And so initially, when we went about writing this paper, one of the ideas that we had, or I had, was that we should compare the leakage rates that different people were predicting. And it turns out that we couldn't find such rates, so they're lacking. If you go into literature now, based on this lacking, we were obviously not the only ones to notice, because there is now, for example, a European Union project called Detect that is finishing, that was focused on measuring these leakage rates. So I'm not saying that it has never been done. It has been done. It has been reported, for example, I believe for Otway it had been reported, but it's not a common denominator of all, by far, of all of these studies, and somehow it should. And this this slide here I added because I thought it would be nice as well to show during the time of this project. We also did some numerical simulations where we were looking, we looked at two specific depleted reservoirs. One was the Captain Reservoir in the North Sea, and the other one was the Haletz Reservoir in Israel. So both of them are in our table. The Captain Reservoir is listed as Peterhead. And essentially, we were looking as well at the reactivation of in situ faults, the subsidence at the surface and at the top of the reservoir, and we were looking at this very specific case of what would happen if the CO2 that was injected was actually cold instead of, so it would have been compressed. And so when you inject it, you don't only have the overpressurization, but you also have a temperature change. And then there was a question about if that would further increase the probability of having induced seismicity or fault propagation or fracture growth. And we found actually that these effects were very localized. But this is just a parenthesis just to show you the types of results. But it's also an example of how we were not really keen on, or we didn't really think of quantifying leakage rates, because in a sense, in the geomechanics literature, and what I will say now is my opinion, I think that quantifying leakage rates is perceived as looking at the injection process in a negative light. As of already, we are assuming that it will fail, that there will be leak, and we are now just measuring how bad it will be. But it actually it is not, because actually, if in the paper, I also mentioned that there's this interesting study from Italy by Roberts et al. That looks into natural gas reservoirs, and it turns out that natural gas reservoirs are very leaky. So, it should not be regarded as a failure to measure leak. We should just have some sort of an understanding of what leakage rates are acceptable and comparable to natural systems, and which leakage rates are unacceptable. And for example, in a depleted reservoir, if we can detect a very small leak, and if this is within the acceptable range, that should give us some time to mitigate and remediate the situation. So one of the issues that we observed was this lacking of the quantification of the leakage rates and the seismicity development over longer periods of time as well. So a lot of these studies as well were very short framed. They were framed around the period of injection and perhaps shortly thereafter, and after that there was just essentially no information. And if you look at it from the geomechanical point of view, this makes sense, right? You don't want, so you want to investigate the problem at the time where the risk is greatest, and the risk is greatest when you're injecting and maybe straight after. And then further along the line, that risk will decrease and decrease and decrease. But especially if you think of other mechanisms that come into play, capillary trapping and perhaps mineralization and so on, blah, blah, blah. But it turns out that from the financial point of view, this long-term quantification of risk is very important. And the fact that the risk of leakage is assessed in a binary manner, such as, in a sense, yes, it can occur, or no, it will not occur. Once that is fed into a financial model, then the weight of a binary defined leakage event will be extremely high, and then thus making the liability risks very high and making insurance very high, and that then translating into inability to ensure the pilot's sites and inability to ensure the investments, which then leads to inability to fund and closure and on hold and cancellation. So in a sense, the lack of this evidence, this underlying evidence of the long-term quantification has huge implications that perhaps are not that clear to us when we're conducting these studies. And so we also, I mentioned this already, we realized that there's a lack of these geomechanical benchmarks where we have cross-code comparison, and that is somehow also present in the community. People know about this, but we are sort of at the level of benchmarking fracturing codes with fluid flow, but not yet with a full geomechanical analysis. But we will get there. We must get there soon, hopefully within the next 10 years. And we are also lacking field-based validations for a lot of these scenarios. Hopefully, when these benchmarks are developed, the next step will then be to have a field-based validation. So there are, of course, some sporadic and specific field-based validations. For example, the result that I showed about the subsidence, this was directly compared against the field, and it was matching. And the reactivation of the faults that we modeled, for example, was also broadly in line to the seismic behavior that was observed. So I'm not saying that this is completely lacking, that it doesn't exist, but there is a need to have a cross-validation across different scientific groups, across different codes, to understand how that predictability is also reproducible by different groups. And yes, exactly. So, and then we come to the trickiest part of this study, and I guess the newest part of this as well for me, which was the public perception. And CO2 sequestration is very much present in the news and is very much present in sort of the green energy cycle plans of Europe and of the UK as well. And the question, of course, is what affects how public perceives CO2 sequestration, right? Of course, when people read articles, they are affected by this, but what in these articles, other than their negative or positive tone, affects their opinion? And it turns out that that in general, it can be scientifically said that the acceptance of CO2 sequestration is tied to the perception of benefit. So people will want CO2 sequestration to be implemented if they can directly understand how they will benefit from it. And that might sound sad or might sound logical and obvious, but it is so. So we have to somehow highlight that. There's not much geomechanics can do about that, but this is just a fact. It is subject to high-profile public opposition, which then is related to strong regulatory frameworks. So it has also been observed that in this social science literature, that strong regulatory frameworks usually follow strong, high-profile public opposition. So they're both tied, and one is the expression of the other. So by regulating public perception, you can also influence the regulatory framework that you will later face. And in many of these cases, like in the case, for example, of the EU, the regulation that they have is very risk averse. So they want absolutely no risk of leak, for example. So there's some work that needs to be done to try to demonstrate at a larger scale to regulatory bodies that there is some degree of acceptable risk, and that hopefully will then feed back into public perception. So when the public read about risk-averse regulation and strong regulatory framework, then that feeds back into their negative perception of the technology. So it's like a catch-22 sort of a situation where both of these are somehow also indirectly fed by evidence-based research that comes from these pilot sites, for example. And the other thing to mention here, also in the broad sense, is that climate change acceptance is paired to public perception. So anything we do to try to convince people that climate change will happen will also help us to convince them that we need CO2 sequestration. And one thing here in this this second slide that I have here, before I go into these four descriptors, is that the UK support for CCS is actually rather high with respect to other European and other countries, like the USA and Canada. This comes from Whitmarsh et al. From 2019. So co-authors also resulting by our co-authors, and this paper was also the result of this joint project. So what does it tell us? That we're not in such a bad situations, but there is still a lot to be done from the point of view of evidence-based to be in the position of reviving a project of CO2 sequestration in the North Sea, for example. And of course, when we look at the press, negative press that irrationally ties, for example, earthquakes with CO2 never helps. But the effectiveness of these on the public perception are tied to four different variables. So awareness, we mentioned that already. It's important to be aware of climate change, CO2 sequestration, what it is, what it's for. If they don't know what it is, of course, how can they support it? Then also very importantly, also in the UK, is trust. So people will want to hear the information from sources that they trust. And in the UK, people trust in first instance academics, which is good news to the audience here. And these are the people that are most trusted in terms of information about safety, then followed by the government, followed by industry. So it's very important in a sense that this academic opinion about CCS is accurate, right? And of course, face-to-face contact helps to increase acceptance of CO2 in these sites, and it was shown in many of these pilot sites that didn't face opposition, that face-to-face contact had been there from the beginning, involving the communities in these decisions and so on. So we know this from a number of other technologies as well, so from nuclear storage and so on. So for example, in Israel, where this technology, where the project is successful and is still working, there was a close face-to-face interaction between people from the project and people from the government and local communities and so on. So it was quite good. However, this doesn't always it is not sufficient to make this work, because there are other examples like in Barendrecht where this involvement was there, but it still was it didn't conduce to acceptance. And then we already talked about how liability plays into this, and I should mention as well that public perception also feeds into liability, because the people that are evaluating liability will also have an opinion that they will have perceived as members of the public that will also influence their decision. And underlying all of this, we have the fear of leaks, the fear of pollution through those leaks, so ocean acidification, or a sort of Bermuda-style triangle event where the whole town dies because of a CO2 leak, or other common ones where, oh, you will inject this CO2 and it will cause a huge explosion and we will all die. So there are many rational fears, but also irrational fears tied to leak, which all need to be taken seriously and addressed by scientists. So so this we mostly already talked about. We also should mention as well that the detailed knowledge of technology does not necessarily affect perception. So it's not about knowledge, but about affecting those that the public trust, to give them the message with the information about whether they should or whether they should not accept this technology, and whether this will bring them benefit, be it environmental or economical, or perhaps mental, or it could be anything really. And another important message here as well, and I know that I'm already starting to run out of time, is that it is very important to decouple the message of sequestration from the oil and gas industry, because in many cases, many of these fears that were also mentioned in these public perception studies were that CO2 sequestration is a technology to prolong the hydrocarbon industry, and it's a technology that will enable the hydrocarbon industry. And that rhetoric is very much tied to the enhanced oil recovery sort of ethos. And so here we try to understand how we can reformulate this technology so that it can be tied to other technologies, like, for example, the production of steel or the production of cement, that are two different technologies that rely on that produce large amounts of CO2 and rely on CO2 producing sources of energy, and those two, and also emerging producers and emitters of CO2, like for example geothermal energy. So in many cases geothermal fluids come loaded with CO2, part of them, and other gases. Part of those can be potentially re-injected, but in certain cases this cannot be re-injected. So a shift into a large-scale geothermal would increase significantly CO2 emissions. Although it is considered a green and a renewable technology, it would still need to be tied to CO2 sequestration in a lot of the future scenarios, not in all scenarios, but in a lot of them. And mining, of course, will go through a huge growth process now, whereby it will need to create all the metals and minerals to feed into the renewable revolution, and all of those mining methods are very CO2 intensive as well. And this is my sort of one of my final images. It sort of brings everything together. So you see here, you have the pilot sites, and they're tied to the characterization of rocks and the simulation, which constitute the evidence. I think that that's really clear to us. And that subdivides into two that I've separated here, the academic argument from the academic opinion. So you have some academics that are the ones involved in the work and that perhaps understand the work and that are explaining the work. And then you have other academics that might be trolling over existing work and forming their own academic opinions. And these are the ones that are most likely to then feed into public perception. So, and these academic arguments, they also feed into the government regulations, which we know also have this two-way relationship with the public perception. So they'll become stronger if the public are sort of claiming it, and they will become laxer if the public are more lenient, and so on. And these all then feed into this financial cost. But this financial cost is important because it feeds back into the feasibility of these pilot studies, which then feeds back into the creation of the evidence. So a lot of this is interconnected, and it's important to realize these connections. And underlying all of this is the need to understand leaks in a much better way, much more so than seismic, than induced seismicity in this context. So I'm now going to close the talk. I will mention a couple of things. Although there is a vast literature in geomechanics, this is generally focused on induced seismicity, thermal stresses, and injection pressure constraints. There are very little studies that look into leak. And the leak and the fear of leak and the perception and the quantification of leak feeds into real and perceived risks of CCS. So it has a two-way feeding capability into this risk, both through the public opinion, so through this academic opinion and this academic argument, which are different. And we need to perform long-term quantifications of leakage, estimate leakage rates, and analyze potential domino effects. This feeds into a number of different types of risk. But we also need to do other things that are not related to public perception, and I'll mention them here, which is very importantly, we need to understand what the potential effects of heterogeneities are in the sites, so that there are not huge discrepancies between the scenarios that we model and then the real case, the real scenarios, because then if those discrepancies do arise, that really then dents the capability of the public to believe in the value of our evidence. And of course, eventually this can then be combined with monitoring to then further increase the acceptance of the technology. So they all sort of feed into it. I just add here this slide because I think it's important to mention that since we wrote this paper, there are a number of other depleted reservoir projects that took off or that are about to take off. One of them is Longship CCS in Norway, another one in Denmark, and there are some others across the world as well. And at the same time, I wouldn't want to claim it's because of COVID or in any way related to it, but one could wonder how the need to incentivize the economy after what we have been through will perhaps lead to the support of industries like coal-based mine plants and wood-burning power plants that would really benefit from being paired to CO2 sequestration, so that if they are planned and set out to work, they don't contribute significantly to emissions. And finally, it's really important to really keep in mind that there's a really strong tie between carbon sequestration and the renewable industry that is now booming, and that I don't think we should sell CO2 sequestration as a transition technology, but rather as a future technology that will help us really make this renewable transition sustainable on the long term to meet all the material and metal demands that will significantly increase during this boom. And finally, I'd just like to acknowledge our sources of funding, the EPSRC and NERC, and through the BGS, of course, and of course as well, I'd like to thank the Royal Society for funding me as well during this time. And thank you very much. That was my last slide.
Great.
I hope you heard my talk.
Yeah. Yes. Over to me, is it JP? Yes, I guess it is. Can everyone hear me? Right, well, thank you very much, Adriana. That was really very interesting. So far, we only have one question from JP on the list of questions. So could I encourage everyone who's in the audience to type their questions into the live event Q&A, which is kind of like a chat associated with Teams event, so that I can convey those on to Adriana. The question from JP is, on the modelling benchmarks, in your position, it would seem you could propose the benchmark simulation content. What are the boundary conditions for the fault-generated leak? And you could therefore formulate in the end a leak quantification model. Are you planning to form a group to design the benchmark? Like the, now, can I say it, Decovalat Lex? You probably know what I mean, even though I can't say it.
Yeah, so I think that this is an interesting idea. I think it's definitely something that the new generation needs to do and to establish. I'm not sure if I will lead it, but I definitely think we need to incentivize the different stakeholders to try to finance or to fund a program like that one, because if we can formulate it in a smart way, it can also feed into other types of subsurface technology that have geomechanics and fluid flow at their heart. Yeah.
Okay, thank you. So following on a little bit from that discussion, I'll ask a question of my own. How likely is it that there will actually be a leak if you fracture the caprock of a reservoir? Because we know from the filling of oil reservoirs that it's normally a sequential process. Obviously, you have various sedimentary layers, I hope the geologists will excuse me, where you have sealing layers, with more and permeable layers, and you get this kind of sequential fracturing of a caprock, flow of the fluid into the next porous and permeable layer, a build-up of fluid, and it's only if you have a series of leakage events that you potentially get leakage to the surface, which is what we're trying to prevent.
That's right. So I was actually going to add a slide about this, but then I thought my presentation was already very long, but I am happy to comment. Yes, we're always assuming that we don't have a single caprock, but usually we will have a system of perhaps baffled caprocks and that are stacked. And so the leak is of very low probability, but a couple of things to mention are that when we talk about leak, we are actually talking about the event of the migration of fluids there from the storage site there all the way up to the surface or the marine environment. So we're assuming that if the fluid percolates through the caprock into the next layer, we can assume that that's a migration event, but actually that fluid needs to reach the surface to actually be considered a leak. And if we look at the geomechanical evidence, the probability of such a leak happening is very low. However, the social perception is an irrational act. So they will think that a leak is just simply like that it is essentially as easy as it is for a bit of water to come out of a pipe and then to go through the walls of a house and then to go into your kitchen floor. This is how they will see it. This is how they will perceive it. And from the financial point of view, if this is a financial risk to my operation, I will just want to understand, if it happens, what will be the time scale and what will be the volume of water that I should expect, and what size will be the lawsuits that will be formulated against me, and how much money will I be liable for? Will I have to remediate an entire town, or will I have to compensate an entire region of a country, or what's the scale? So there is a difference between the rationality of quantifying a leak mechanically and from the geological and fluid flow point of view, and there has to be a way of building a bridge between that quantification and the irrational perception of the implications of these leaks. And so it's important to quantify them. That's sort of my message is.
Okay, thank you. We have got one more question, and then I think we'll have to draw the seminar to a close. It's from Martin, and he asks, to what extent is CCS limited by public perception rather than financial barriers? And he's of the opinion that it's actually financial barriers that are preventing the deployment of CCS. Yeah,
so I agree. And but the point that we try to make in the paper is that public perception feeds into financial barriers.
Yeah. Okay.
So it is a misconception to think that financial that there is no link between the financial barrier and the perception, the public perception.
Okay, thank you very much. I think yes, we could follow on from that, but I'm aware that it's 1 o'clock and people have other meetings to go to. Thank you very much, Adriana. That's been really very interesting and thought-provoking. We look forward to hearing more about maybe your formation of a group to design the benchmark in the future. And I will draw the seminar to a close now, but remind people that next week, same time, same virtual place, we have Dr. Laura Gregory from the University of Leeds providing us with our seminar, and she'll be talking about earthquakes in central Italy, quantifying the past to understand the present. So please come along and enjoy that. Thank you again, Adriana, and thank you to the audience.
Thank you. Bye.
Bye.